I usually have a pretty good idea about the kind of music I want to create. The problem is, to get it right, I have to master all the instruments and the techniques by myself. Don't think I haven't tried. It works much better when I get great musicians to play for me.
Kenneth, let's add a little color.
They have all the talent and the years of experience to turn my ideas into great music.
A G pedal bass.
I don't have to teach them from scratch.
Put in a vent, one of those G chords.
All I have to do is give them a set of high-level instructions, and they take care of all the complicated details.
Hi, I'm Philippe Kahn. Ever since I was a kid, I've been interested in making complicated things work. Although I love music, my field is software. Most software today is made up of too many unrelated parts. It's not really reliable, and it's clumsy. Much like trying to play all the instruments in the band by yourself. Now imagine another kind of software in which different parts of your program bring some intelligence to the job. They know how to interact with each other, just like the musicians in my band. Sound impossible? It's not. Let's start by examining the evolution of computer hardware.
Computers started out clumsy. Made of vacuum tubes, they took up lots of space for very little function. Then we progressed to transistors, which were smaller and better. But it still took lots of them to do anything interesting, and if one failed, then you had to test for a long time to find it. Look at this mess of transistors.
But that's just where we are in software development today. The ideas I'm about to discuss represent as powerful a change in programming as going from hundreds of thousands of transistors to a single integrated circuit.
This is a place where you can buy all the components you need to put your own computer together. In the future, you'll be able to buy a ready supply of off-the-shelf software components. You'll assemble them to create your own applications.
All these programs and design tools that I'm introducing to you today are based on a concept called object-oriented programming. And it might change the way you think about software engineering. You're going to be hearing a lot of new terms in this video.
Terms such as encapsulation, inheritance, and polymorphism.
But let's have a little fun. This is a movie after all, and we can do whatever we please. Wow! A 1960 Corvette. They used to call this the pocket rocket. Let's take it for a spin. And while we're doing that, I'll be telling you about the basic idea behind object orientation. Let's start with what's an object. Now, in real life, like in programming, an object is something that you can describe. Something that's got attributes and behaviors. Take this classic Corvette. It's got attributes. It looks real nice, comes in many colors, mainly red. It also has behaviors. Now, the Highway Patrol knows a lot about those. You don't have to know how the engine works to drive a 60 Corvette. Its designers have put a lot of functionality in which is invisible to you.
When you turn a knob, the radio comes on. Pull a switch, and the headlights come on.
All this hidden functionality, which is bundled with a state of corvetness, is called encapsulation in our object-oriented world. The better designed all this stuff is, and the more tightly it is integrated with the state of the object, the better the object works. In the future, I believe that everyone will have something that looks like this. Let's use it and learn a little more about what object orientation means.
Everyone understands windows and icons. These icons are objects. They have hidden functionality in that they open like this. Let's now open the Objects folder. And now let's go to the car demo.
All this knowledge is encapsulated in the objects, just as my fellow musicians had the basic chord pattern to our songs encapsulated in their memory. Now let's go back to our idea of objects. In object-oriented programming, objects are organized into a hierarchy of classes. It works like this.
Let's open the classification tree for sports cars. Here we can see that our vintage Corvette is part of a larger class of objects called sports cars. Each object is related to others by its characteristics. Cars have tires, engines, and drive on roads. As I move up the hierarchy tree, we see that cars are part of the class vehicles, which include boats and planes and take people and goods from place to place. And these belong to a larger class of objects called machines, which all require an energy source and are manufactured. Machines are all physical objects, which in turn are all objects. Moving from the top of the tree to the bottom, we move from the general case to more specialized objects. In object-oriented programming, we use this technique to design our software objects.
Again, this way of looking at things is a hierarchy of classes. It's the way scientists have made sense of the world around us for years. This is my friend Sky. She's a mammal. She's also a canine, she's a dog, she's a border collie. Sky just had a litter of 4 puppies. Dad's a black lab. Genetics tells us that half of the characteristics of each puppy were inherited from mom, the other half from dad. This is Puffy. Puffy looks like dad. Now Skippy here looks like mom. In programming, as in nature, this sharing of attributes within a class of objects is called inheritance. In the design of anything, inheritance buys you a lot of efficiency. For example, take car manufacturers. They've agreed a while ago to actually standardize on having gas pedals on the right so that every time you go and rent a car, you don't need to relearn the art of car driving. Thank goodness car design is not as random as traditional programming is. By contrast, if you use inheritance in your program design, important traits are built in at high levels. Things that are conceptually similar work in a similar way.
See these different icons? One's a graphic, one's a video clip, and one's a document. They are all objects. In an object-oriented system, all objects respond consistently to a certain set of commands. Now let's look at an object-oriented application. This is an online multimedia news service. It continually gathers the kind of information that I'm interested in. To the user, all of this works as expected. All I do is choose the story I want with one simple command: show world of objects. The show command allows me to view a video clip. But wait a minute, I've seen this video someplace before. The same command allows me to read an article. Show Billy Hart he's got the beat. This is a story on Billy Hart, the great jazz drummer who played in my band. Or it lets me look at bitmap graphics. Show Canine Kingdom. Wolves? Dogs? Border collies? Hey, that's my friend Sky. It all works the way you expect it to because the show command knows how to adapt itself to the appropriate environment. Show classic Corvettes. A video clip shows a piece of video. Show software by components. And a text icon shows me an article. This works because all of the objects have inherited the ability to respond in their own way to the show command.
This concept that the exact meaning of the command is packaged with the specific object is called polymorphism. Polymorphism in the physical world works like this. Every animal has to eat. Here's Sky. But the verb eat in the various classifications of the animal kingdom means different things. Watch this. All animals eat, but do it differently. That's polymorphism. Why is this an important idea in programming? That's because it allows us to use a simple command like print, which we all understand and we can all remember, and get exactly what we need. This works even though the kinds of things we want to print may be different. Now, let's talk about how this object-oriented thinking helps a computer programmer. Since the task of computer programming is to build something functional, let's follow the metaphor of architecture.
When writing our programs, our goal is to design something structurally sound. Well-architected programs are built on top of a solid foundation using previously tested and reliable components. By contrast, poorly designed programs tend to fail when subjected to stress. This happened to a lot of buildings in California during the 1989 earthquake. But other buildings, like these skyscrapers in San Francisco, swung on rubber posts for 30 minutes after the earthquake but stayed standing.
Well, how can we build these safety features into our program? The key is to focus on proper architectural development. Now, I've been telling you object orientation is the wave of the future. Here's what some of my colleagues have to say.
Object-oriented programming is a different way of organizing state and program code. What it does is to take all of the procedures that are concerned with the format of the data and to seal them away so that you don't have to worry about them when you're building a much larger structure.
If you define something like a chair for some knowledge processing program to use, and then you say, well, what about a couch? Then the natural thing is not to start all over, but it's to say, well, a couch is like a chair, only it's wider. And then in the object-oriented tradition, the chair automatically still has the 4 legs and the 2 arms and the back and the seat and all of the things that it had before, except that now it's wider.
In an object-oriented system, you divide the computer into things that are like little computers. They have the same power of the computer. You can divide those computers into little computers, and so on.
The design phase that some people have tried to sort of superimpose over a traditional programming language, and not always with very much success, becomes a natural part of programming because you can separate the process into design your concept, find their relationships. Now, when you've got a good framework, write your program.
It's a rather natural representation and consequently makes the programming relatively easy, makes it relatively easy to modify the program, and makes the program, even a very large system, much more comprehensible than it might otherwise be.
You wind up writing less code. Your design can be conditioned by a master architecture that's already present. You have a collection of concepts that you can extend without having to add new ones. And you don't have to worry about the representations that you're employing until you actually have to deal with some optimizations of one kind or another.
The primary benefit is to be able to develop things incrementally, step by step, not needing to understand things in advance that you're not even going to use in the future. In ordinary programming, everything has to be laid out very precisely, and a lot of that precision is first expensive and painful and unpleasant, and most of it isn't necessary.
I think the biggest benefit of object-oriented programming is that it speeds up development time greatly, and the amount of code that you have to deal with is typically a factor of 10 smaller.
Our problem has always been that people have adopted C++ faster than we could educate them to use it well. The growth rate has been astounding. Over the last 5 years, there's been a doubling every about 7 months.
True progress comes when you find a way to unite ideas. A traditional example is that one found negative numbers and could unite them with the natural numbers into the whole numbers and see that the same laws apply to all of them. That's a true simplification of matters. And in that sense, I think object-oriented programming should also be integrated into what we have already.
I think for anybody who's a skeptic about this, what they should consider is whether it's worthwhile trying out something new because it might change their whole way of doing things. And people who are not interested in trying out new ways that might help themselves are often left behind.
See this stuff? It's good to eat, but that's not what you want your code to look like. Spaghetti code will never give you reliability and extendability. Object-oriented programming is the solution. It's clearly technology worth looking into. I've been throwing a lot of ideas at you. The bottom line is, if you focus on an object-oriented architecture, your entire task as a programmer becomes much easier. Object-oriented architectures make it easy for programmers to speak the same language. They can consolidate their ideas without having to start from scratch every time. If you think of it as music, the parts of your program come together and interact like talented artists who've been playing with each other for a long time.